Okay, so the second part of section 2.3, higher order derivatives. Take a few minutes, please. Pause the video and attempt this warm-up. We will go over the answers tomorrow in class. Okay, so what is a higher order derivative? So a higher order derivative is anything past the first derivative. So if I ask you for the first derivative of a function, we know the notation for that is f prime of x. I use this often, the derivative of whatever function follows it. So any given function f, you could see dy dx. We also said y prime. That's another notation we use often. So then the second derivative would just be the derivative of the first derivative. So f double prime of x, it would be written as d squared over dx squared of a given function. You could also say it as d squared y over dx squared, and so forth and so on. So third derivative, f triple prime of x, and the fourth derivative, at the fourth derivative and after, you would just write it as whatever order derivative you're looking for. So for the rules for the nth, and this would be, it should be a 4. So the nth derivative, again, that's where you just write the number. dny with respect to x to the given nth order, the nth derivative with respect to x of a given function. Alright, y to the n if we use that. So just some of the notation to get used to. And we'll talk about the importance of higher order derivatives after a couple examples. Alright, so find f triple prime of x if f of x is equal to x to the 7th minus 3x squared plus 2. So in order to get to the third derivative, we have to start with the first. Using the power rule here, 7x to the 6th power minus 6x. The second derivative, we now just take the derivative of the first. 7 times 6, 42x to the 5th power minus 6. And then lastly, the third derivative, 42 times 5, 210x to the 4th minus 0. So not meant to be difficult. It could also be asked for this. Find the 6th derivative if we know the 4th derivative is already 2x plus 1. Okay, so then the intermediary, the 5th derivative, using the power rule, would be 2, and therefore the 6th derivative of any constant, is 0. Alright, so if our function is cosine of x, we know the first derivative of the cosine function is negative sine of x. The second derivative, negative cosine x. The third derivative is positive sine x. And then the fourth derivative is positive cosine x. So if you remember this type of behavior, it was, say, if you were asked for something like I to the 21st power, so last year from pre-calc, we can use that same modular, is what we refer to it as, to find, if I ask you the 50th derivative of cosine of x. And this, let me just make the notation right. So I want the 50th derivative of the cosine of x. Well, I wouldn't expect you to write it out 50 times, but we know the behavior of the cosine function. So it repeats in intervals of 4, 2, and remember, it's the denominator that tells us, or not the denominator, excuse me, the remainder that tells us where in the pattern, I would find the 50th derivative. So think about what this says. The 48th derivative would be equal to cosine. So this would be the 49th, the 50th derivative. So the denominator, I keep saying that, I'm sorry. The remainder, this is the equivalent to the second derivative of cosine of x. And what's the second derivative of cosine? Negative cosine of x. So that would be our answer. Okay, so again, the remainder, I keep saying denominator, sorry. The remainder tells us which derivative in the pattern to look for when we're looking at something that has a repeating behavior. This same method could be used for any nth derivative of the sine function as well. Okay, the pattern's different, but they will, by the fourth, repeat itself as well. Okay, so why the need for higher order derivatives? So we've looked at the position function. We represent that with s of t. Then we said the rate of change of the position function was the velocity function. Now let's look at the rate of change of the velocity function. So change in velocity with respect to time, that's our acceleration function. Okay, and I talked about this in class today. So we can find any average rate of change. So the average acceleration is the change in velocity with respect to time. The instantaneous acceleration is when we have to take the limit as the change in time approaches 0. So v velocity of t plus delta t minus the velocity all over delta t. So the acceleration function is the rate of change of the velocity function. The instantaneous acceleration is found by the first derivative of the velocity function, which is really the second derivative of the position function. Okay, and we'll look more and more and more at the relationship between position, velocity, and now acceleration the further we get along in the text. Right, so your position function is negative 16t squared plus 3t plus 4. The velocity function would be the first derivative of position using the power rule, negative 32t plus 3. And the acceleration function, which is now, we know, the first derivative of the velocity, when we derive this, negative 32. Which makes sense. And I know we talked about this with those of you that might not be in physics, but acceleration is constant. So this is our acceleration due to gravity. So it makes sense why the value would be negative 32. Now let's talk about units though. Velocity is feet per second. If it's the change in velocity with respect to time, so velocity's units are feet per second, our unit of time is seconds, so acceleration's units are feet per second squared. So from the given function, if I ask you for the velocity at 1 second, plugging it into the velocity function, negative 29 feet per second, and the acceleration anywhere is constant. So the acceleration of this particle would always be negative 32 feet per second squared. All right, now what I would like to do is a couple of problems with you from the book. Okay, page 127. Number 74, I heard some of you still talking about having issues with this from the other night. And the directions are: determine the point at which the graph of the function has a horizontal tangent line. Alright, let's break this apart for a minute. Horizontal lines, we know, have a slope of 0. If I'm asking you about a tangent line, we know that the slope of tangent lines come from the derivative function. So for these problems, you're finding where the derivative is equal to 0. Alright, so we want the tangent line. We get the tangent lines from the derivative of the function to be horizontal. So we're looking for where the derivative equals 0. So the function in 74, x squared over x squared plus 1, using the quotient rule to find the derivative. Bottom function times the derivative of the top function minus top times the derivative of the bottom, all over bottom squared. I get 2x cubed plus 2x minus 2x cubed, all over x squared plus 1. These cancel, so our derivative function, 2x all over x squared plus 1, quantity squared. Where is a rational function equal to 0? So where does the derivative equal 0? When the numerator is equal to 0. So x is equal to 0 is where there would be a horizontal tangent line. To get the corresponding y value, we have to plug 0 back into the original function. So f of 0 would give me 0 as well. So to answer the question, determine the point at which the graph has a horizontal tangent line. Horizontal tangent line at the origin, at the point 0, 0. Okay, same page, 127, number 62. Let's write the equation of a tangent line at the given point. So my function here is sine x times the quantity sine x plus cosine x at the point pi over 4, comma 1. Okay, equation of a line for tangent lines. Automatically associate that with point slope form. So y minus 1 equals m times x minus pi over 4. And the slope of the tangent line comes from the value of the derivative at the x coordinate. So let's find the derivative of the function. Now I'm not going to distribute the sign because that's a different rule, and I'll explain that when we get to section 2.4. But I'm going to keep it as the product. First function times the derivative of the second function. Derivative of the second is cosine x minus sine x plus the second function times the derivative of the first function. Derivative of sine is positive cosine. Alright, so now plugging in pi over 4. So sine of pi over 4, square root of 2 over 2. This works out nicely. Sine and cosine are equal at pi over 4, so that would be a value of 0. Again, them being equal, square root of 2 over square root of 2 plus square root of 2 over square root of 2, and then times the square root of 2 over 2. So this would be, that goes to 0. When I add these together, I get 2 root 2 over 2 times square root of 2 over 2. They cancel, so I just get a value of 1. So what does that represent? The slope of the line comes from the value of the derivative at the x coordinate, so the slope would be 1. So I plug the slope back into my point slope form, and there's my final answer. And I guess I'll put this here. This is f prime of pi over 4. Okay, and just a reminder, your homework assigned in class, page 127, numbers 65 and 67. Have a good night.